Hello friends, welcome to my channel. Let's have a look at a problem 2340, minimum adjacent swaps to make a valid array. So this is a new problem, and actually for this problem the code is not that essential, but the logic is what we want to convey. So the problem asks us to return the minimum swaps required to make a nums array a valid array. So a valid array is the following. So the largest element is at the rightmost position in the array, and the smallest element is at the leftmost position in the array. So here are two examples. So example 2 is sort of trivial, and example 1 and the problem statement explained it in details. So here the constraint is that the length of this array can be up to 10 to the power 5, which is a decent large number. So with that said, let's explain our reasoning or method. So the method here is nothing but simple counting. So the idea is the following. So we're going to find the index I for the minimal element from the left, and then we're going to find the index j for the maximum element from the right, and then we just count directly how many swaps we need. So there are three cases. Let's treat it or analyze it one by one. In the first case, if the index for the maximum element and minimal element are equal, then we're going to return 0, because in this case the array is a constant array. So in the second case is the case I is less than j. In other words, the smallest element we met first from the left with an index less than the largest element we first met from right. So in this case, we just need to swap the minimum element at index I to the left end, and swap the maximum element at index j to the right end. So the number of swaps is nothing but I minus 0. So this is the swaps needed to make the minimum to the very left. And n minus 1 is the right end index, so minus j. And the n minus 1 minus j is the number of swaps needed to put the maximum element at index j to the right end. So that's the case 2. So the third case is that I is greater than j. So for this case, actually we can reduce the situation to case 2. So let me first share the total number of swaps, then we explain how we get this number. So the total number of swaps needed is 2 times I minus j minus 1, then plus j plus n minus 1 minus j. So we can understand this number into two steps. So we decompose this whole procedure. First, we are going to swap I and j. So the number of swap needed for this operation is 2 times the difference minus 1. So we can think of, we first swap I to the position j, right? So this needs I minus j swaps. So this is the first bracket here. And then now after this, j is at position j plus 1. Then we want to swap the number at j plus 1 to index I. So this needs I minus j plus 1 swaps. In other words, the difference of indices. So this is the number of swaps needed to swap the maximum number and minimum number. So after this, actually we know the minimum number appears at index j, and the maximum number appears at index I. Then we just need to swap the maximum number and minimum number to the right and left end respectively. So the number of swaps needed is nothing but j, right? J to the very left, that is j swaps, and n minus 1 minus I. So we put this I into the index n minus 1. So that's the j plus n minus 1 minus I. So the total is 2 times I minus j times this j plus this g plus m minus 1 minus I. In total, this is the number, right? So actually, this problem itself, it's not very complicated, but it's good to notice that. So if we have two index, so the key point to notice is that if we have two index, let's say I and j, then if we want to swap these two elements by just swapping the consecutive two elements, so the number of swaps needed is 2 times the index difference minus 1. So that's the thing we should be aware of by looking at this problem. So with that said, let's quickly write the code. So this is actually very routine. First, let me track the minimum and maximum index. So let's call it m index and this capital M index. So m and m will be the minimum of nums and the maximum of nums. So we're going to look at the the little m index from left. So it's just the nums index. So the little m. We're going to look at the capital M index from the right. So it's nothing but nums. So we reverse it, then look at the index for capital M. We're going to use this n minus 1 minus this number, where n will be the length of nums. Let's introduce this variable n for convenience. So with that said, we just need to consider the three cases listed above. First, if this m index corresponding to I equals capital M index. So this means that we have a constant array. So we're going to return 0. Otherwise, if m idx is less than the capital M index, then we just need to move the little m index to the very left and move the capital M index to the very right. So the number of swaps needed is nothing but m index plus m minus 1 minus this capital M index. So that's the second case. The third case is that the little m index is greater than the capital M index. So in this case, as we analyzed, we just need to return 2 times the index difference, that is m index minus capital M index, then minus 1, this is the first term, then plus the smaller index, that is m index, then plus m minus 1 minus the larger index. That's it for this problem. Let's do a special case check. Yeah, it passes the example 1 in the problem. Now let's do a generic case check. Yeah, it passes the generic case. I guess that's about it for this problem. So if there is something we need to be aware of, I would say that's the key here. So if we want to swap two indices ij by the constraint in this problem, the swaps needed is 2 times the index difference minus 1. So in other words, the needed swap is always an odd number. So this is an interesting observation. So you can actually apply this observation to other problems. So I guess that may be one of the benefits of this problem. Thank you very much.